Hello again. So we took a look at a really big kinetic problem because it helps, and it kind of took all the different possibilities of things that we see with regards to kinetics and put them into one problem. And here I'd like to do basically the same thing with the equilibrium problem, which you see over here to the right, number 4. So A is an unidentified nonmetal. It forms a salt with an unidentified metal M with the formula Ma2, which is slightly soluble in water with a KSP of 7.2 to the -9th at 25 Celsius. So letter A, write the net ionic equation for the dissociation of this salt. So this is for A. So when this guy dissociates, we're going to go Ma. Now, because we are dealing with dissociation and I want to make sure that we are as clear as possible, I'm going to include my states of matter here so you guys know exactly what I'm talking about. Keep in mind on the AP test, states of matter are not required. So when this dissociates, of course, it is going to break up into its component ions. Now with Ma2, chances are your M is a -2 ion. In this case, it's going to be aqueous. And we're going to end up with 2. Sorry, that's a +2. Did I say -2? And we have 2 ions of A, which is going to be our anion, also aqueous. Now, this could have been something like, let's say, lead-4 oxide. So this could have been a +4 and a -2. No way without knowing any more than that we would be able to do that. All right, but charges aren't going to really affect anything else that comes after that. So letter B, write the equilibrium expression for the dissolution of this Ma2 stuff. So if we're talking about solubility, then our K value should be a KSP, or solubility product. You'll notice we get, when this dissociates, 1 ion of M. So it, in effect, has a coefficient of 1. And we get 2 A ions. So coefficient of 2, that one is going to get squared. And there is your equilibrium expression. Ta-da! Letter C, determine the concentration of a saturated solution of Ma2 at 25 degrees. So the value that we have for KSP indirectly tells us how much of this stuff can dissolve. So at 25 degrees, our K value is 7.2 times 10 to the -9th. And keep in mind, once again, for equilibrium units, we tend to leave out of our calculations. And we need to know, at equilibrium, what will the concentrations of our ions be? So how do we do that? Well, we know that up here, we're getting 1 ion of M and 2 ions of A every time that this stuff is dissolving. So initially, before we added the salt to water, we had 0 concentration of both of those. When we add it, I'm going to add some unknown amount of M, because some unknown amount, some very small unknown amount, is going to dissociate, leaving me X concentration, or X molarity worth of M ions. However, because of the 1-to-2 ratio here, we're going to get 2X worth of A. So this is basically my ice table here. So at equilibrium, what do I get? Well, X and 2X. And with KSP problems especially, you should get to the point where you don't really need to write out a full-blown ice table. You should just go, all right, there's 1 of these, 2 of these, so this one's going to be X, this one's going to be 2X, and of course, because of the coefficient, it gets squared. And some people go, wait, we double it and we square it? You betcha, that's exactly what happens. So on the right-hand side, 2X quantity squared, don't forget the 2 is squared as well. That gives us 4X squared times X. So over here we have 4X cubed, still equal to 7.2 times 10 to the -9th. So we divide by 4. We then take the cube root, and we get 1.2 times 10 to the -3rd molar. All right, now that is your concentration of the Ma2, the original salt that we're trying to dissolve. Keep in mind, a problem could say, what is the concentration of A ions at equilibrium? Notice a 2 there, no coefficient over here. So if that were the case, we would double this value if it asks for the concentration of A in the solution once it was saturated. All right, letter D, what is the concentration of A ions in a saturated solution of Ma2? Whoa, holy moly, I just predicted the future. So, letter D, we're just going to take our 1.2 times 10 to the negative third, and we are going to double it. And why are we doubling it? Because there are 2 moles of A produced for every 1 mole of Ma2 that dissolves. So that gives us 2.4 times 10 to the negative third molar. Ta-da! All right, now in this particular problem, letter E gets into some acid-base stuff, and we haven't dealt with that yet, so I'm going to skip that one for now, and we are going to move on. Let me get myself some more space to write here, so we're going to jump E and go right to letter F. So notice F. Above that says HA is a gas that reacts with oxygen as shown below. So we're still talking about this ion A. And at 125 Celsius, the reaction above reaches equilibrium with a Kp value, so this is a pressure-based equilibrium constant, of 2.4 times 10 to the fourth. We want to write the equilibrium expression for that reaction. So in this case, K would equal, well, we know that products go on the top, and we have HOA on the top, and we have 2 moles of that. So I'm going to go HOA, and that's going to get squared. On the bottom, my reactants, I have HA, and of course you're probably thinking to yourself, what in the world are you doing? Because I'm thinking the same thing to myself. I'm thinking, I don't know what I'm doing, because this is supposed to be a pressure-based equilibrium, isn't it? Yep, it most certainly is. Okay, so we're going backtrack, and I'm going to say the pressure of this stuff, which is going to get squared. Down here, the pressure of HA is going to get squared, times the pressure of oxygen, which will not get squared, because in our reaction over here, oxygen is the one species that does not have a coefficient of 2 in front of it. All right, so there's your equilibrium expression. Then letter G. If 0.2 moles of HOA gas is placed into a rigid, evacuated 2-liter container, calculate I, the initial pressure of HOA in the container. So this is before any reaction happens. So this is going to be straight up gas law / stoichiometry. So we want to figure out the initial pressure of HOA in the container. So we know how many moles there are, we know the temperature, we know the volume, so calculating the pressure, nRT over V. You'll notice this way right here, when using the ideal gas law as well as many other equations, if you look at the solutions provided for a lot of the AP FRQ questions, they will rearrange the equation algebraically before plugging any numbers in. And that's a really nice way to show your algebra and make it really clear to the people who are reading and grading your test. So please consider doing that way. So on top we have 0.2 moles. Now, I don't believe that this one's specified, but we are going to do this in atmospheres. 0.0821 is going to be our R value. Our temperature here of 125 is going to be 398 when we convert it into Kelvin. And, of course, our volume, 2 liters. So you're going to go click in your calculator, plug all that stuff in, and we get 3.27 atmospheres. All right, so that's going to be your starting pressure. And why did we want a pressure? Because in order to do the next part of this problem, we need to know the pressures, because we have a pressure-based equilibrium constant. So we want to figure out the equilibrium pressure of HA. So I'm going to go ahead and rewrite our equation here, because here is a good spot to do an actual ice table. So I'm going to write HA plus O2 is going to give us, and of course this is reversible, 2 HOAs. And our initial row is going to be 3.27 atmospheres of HOA. And of course we have none of either of these left. Now here we're going to be moving to the left, obviously. So we're going to set up our ice table as though we're doing it for the reverse reaction. So if I started off with 0 of each of these, then I know that I'm going to end up increasing by x with this one, and this one will going to increase by 2x. Proportionally speaking, this one is going to decrease by 2x. Now right now we have a problem in that we're dealing with a very, very large k value. So remember, kp is 2.4 times 10 to the positive fourth. So that's kind of problematic because we're dealing with a big k value. But keep in mind here that we're looking at the reverse reaction. So if we're working our way back to the left, we can figure out the equilibrium constant for that reverse reaction and say that it's going to be whatever the kp is here, and we're going to take the inverse of it. And in this case, that is going to give us 4.2 to the negative fifth. So that's our new k value. So we can look at the reverse reaction and treat it as though that's the forward reaction. So what are my final concentrations here? That's my change. Here are my final equilibrium concentrations. I'm going to have 2x, I'm going to have x, and over here I'm going to have 3.27. And you, of course, might say, what happened to the 2x? Well, because we have such a small k value, we know that x is going to be a very, very tiny value. So small that it will be negligible relative to this initial pressure. So our hope is that that's going to be something like 0.0 something, so small that it's not really going to have much of an effect on our map. So what are we going to do? We're now going to take this new k value of 4.2 times 10 to the negative fifth, and we are going to plug it into our equilibrium expression along with everything else. So my pressure of HOA is going to get squared, and we know that the equilibrium pressure of that is 3.27. My equilibrium pressure of HA is 2x, so I'm going to go 2x quantity squared, and it's just plain x for my oxygen. All right, so we plug that in, and we're going to do a whole bunch of algebra, which I'm going to leave to you guys. And if you want to go ahead and double check me, we get an x value of 0.033. As we predicted, it would be 0.0 something. So once again, you can realize that this is a very small value of x, not going to have much of an effect on that pressure right there. However, the question said, what is the equilibrium pressure of HA? So x, you'll notice, is my concentration of oxygen. So I'm going to take this, I'm going to multiply it by 2, and I get 0.000, not 00. Get out of here a second, O. I guess the undo button doesn't like to work. Neither does the writing button. What is going on with this thing? There we go. 0.066 atmospheres of HA. I'm running out of space. I apologize for my handwriting, by the way. It's weird writing on this thing. Last but not least, determine the concentration equilibrium constant, so Kc, for this reaction. So we have this where we go to the delta Ng, or number of moles gas. Oh, I left the R out. Where's my RT? Doop. So what we have to do to figure out what Kc is, and the delta Ng goes over there. Sorry, give me a second. I just wrote my equation completely wrong. You have to forgive me. You don't really have to, but it'd be nice, don't you think? So what we have is Kp equals Kc, and then RT to the delta Ng, meaning change in moles of gas. So if we want to figure out Kc, we're going to take our pressure-based equilibrium constant and divide it by that same value. And of course, this one is in parentheses. So we know what Kp is. We know our pressure-based equilibrium constant is 2.4 times 10 to the negative fourth divided by, we have our RT, and in this case, R has to be 8.314. And our temperature is 398 Kelvin. And in this case, we are going to take this guy to the -1 power. Why? Because you'll notice up here, in our reaction, I started off with 1, 2, 3. 2 of these, 1 of these. 3 total moles of gas. Over here, 2 moles of gas. So I decreased by 1 mole of gas, hence the negative 1. And this gives me 7.9 times 10 to the 7th. And that's it. A little bit of everything in terms of equilibrium.